All right, this is Mr. Griffith, and we're going to be doing a little bit more with the rules of logic. And we're going to be analyzing statements, okay? Find out whether or not statements are true or false. And in this segment, you might want to take a look in your chapter on page 24, example 1.5, where we're talking about analyzing statements and negations. And what it asks you to do is, 1, determine if the following sentences are statements. If so, form their negations, and if not, say that no negation exists. So it starts off by saying the sum of two even numbers is even. So here's one, okay. The sum of two even numbers is even, okay? Well, is this a statement? And the answer is yes. It has a truth value. We'll determine that in just a moment. We're going to find out how to think about it. So sum of two even numbers is even, and then it will form its negation. Now understand this, that if a statement is true, its negation is false. If a statement is false, its negation is true. Negation always changes the truth value of things, okay? Statements are not just true by default. You have to look at them to see. And this is a declarative sentence. It makes it's declarative. It says something, you can determine whether it's true or false. So sum of two even numbers is even. So, well, let's see. Let's try a couple of even numbers. 4 plus 6. Okay, so 4 plus 6. Well, 4 plus 6 is 10. Okay. Generally speaking, we can see that on a number line, okay, where we have things like this, we're going to have an even and an odd, and an even and an odd, and an even and an odd, and an even. And we can see that if we add, if we start off, say, at 0, okay, and here this is 0, Z-E-R-O, and this is an odd number, this is an even, and this is an odd, okay? You can see even is two spaces. Evens are at least multiples of two spaces apart, okay? And so if you increase an even by a multiple of two spaces, you're always going to land on an even number. Well, so this is a true statement. Well, how would we state its negation? Well, stating its negation, we would just simply say the sum of two even numbers is not even. Okay. Another word for not even would be odd if you're talking about even and odd, but then if you're talking about anything else, it would, just simply say not even. Well, how about part B, okay, where it changes this and it says the sum of two odd numbers, okay, so odd numbers is odd. Is this a statement? Yes, this is a statement, okay. Well, what is its truth value? Its truth value is either going to be true or false. Well, let's try one. 5 plus, let's say 9 is 14. Here is a counter example. This is a counter example. And the counter example demonstrates that this is a false statement. Since this is a false statement, we need to make it true. So the sum of two odd numbers is not odd. Okay, so I could, so if I'm going to change that, okay, from false to a true, I could say it is not odd, or I could, if I wanted to, I could say the sum of two odd numbers is even. Okay, so you understand that negation always changes the truth value. Well, how about part C? It says the square of a number is greater than 10. So it the square of a number is greater than 10. Well, now let's see whether or not that's true. Okay. Now remember, this is an is greater than 10. So this is essentially saying it's all the time greater than 10. Okay. So let's see, how about 5 squared? Oh boy, well that's 25. That's certainly greater than 10, isn't it? Okay, well it's true for this. How about 4 squared? Well, that's 16. It's true for that. How about 3 squared? Well, that's 9. Uh-oh. Okay, here we go. 3 squared demonstrates that it is, that this is not correct all the time. It is partially correct. Okay? Now, the thing is that this is not always true. Now a statement cannot be true or false at the same time, all right? But this thing is not always true, okay? So, since it's not always true, really there's not a negation that we can give, except that we can provide some counterexamples. We can say, well, it's true for such and such, or it's false for such and such. What it really needs in order to be a statement that has a singular truth value, okay? A singular truth value, because a statement isn't going to have more than one truth value, okay? For a statement to have a singular truth value, we might need to say is greater than 10 for numbers that are greater than 3, or greater than, let's say, or equal to 4. Okay, and that would make it a true statement. But in just this other one, and I don't think we're going to count it as a statement because it's only only part true. Okay, and since it's only partially true, we're not going to count it as a statement. A statement is either true or false, but it is not both at the same time. Well, how about part D, where it says a parallelogram has 4 sides? Well, we know that that's a true statement, okay? So how would we, and it does. A parallelogram has 4 sides. But to negate it, if we negate it, that would be a false statement. It would be saying a parallelogram does not have 4 sides. Now, how about conditional statements? Okay. Conditional statements are a little bit more difficult. So what I'm going to do is I'm going to give you an illustration. Suppose that I tell my wife, if you wear that red dress, then I will take you out to dinner. Okay, so I've told my wife, here, you know, so here's the value. P is if you wear that red dress, dress, then I will take you out to dinner. Actually, we're going to split this up into two parts, okay? Let's see. You wear that red dress, okay? You wear that red dress. That is our P. And I will take you out to dinner. That's our Q. And here is our conditional statement. Okay, here we've got the P, here we've got the Q, and here, if P, then Q. This is our conditional. If P, then Q. Well, let's take a look at the possibilities. So I can have, if she wears that red dress can be either true or false. And my taking her out to dinner can be either true or false. Well, under what conditions would I be telling the truth, and under what conditions would I be lying if I made this statement? Okay. Well, if you look at this, okay, so she wears the red dress and I take her out to dinner. Well, obviously then I told the truth. If she wears the red dress and I don't take her out to dinner, then I lied. Okay. But what if she doesn't wear the red dress? Now this is where it gets sticky. Well, can you agree that if she doesn't wear the red dress and I don't take her out to dinner, then I told the truth? I think you would be able to agree with that, all right? Because I said if you wear the red dress, then I will take you out to dinner. The problem comes here. And the fact is that with a conditional statement, if P then Q, the guarantee that Q happens, the guarantee that I'll take her out to dinner, is based upon wearing the red dress. If she doesn't wear the red dress, then I can do what I like. I only told her what would happen if she wore the red dress. I did not tell her what would happen if she did not wear the red dress. Okay. So, if she doesn't wear the red dress, and I want to take her out to dinner anyway, I still told the truth. The only way I can lie in a conditional statement is for the condition to be met and for me not to keep the promise. Okay? So the negation, okay, of this would be P and not Q. P and not Q would be a negation to this. Well, let's see if we can show that. Because here's not Q, and not, here's Q and not Q, and this is false, true, false, true. Okay. And can you see that a true and false is false? You know that an and statement is true only when both parts are true. Okay. Well, here's a true and true. Now that's true. Here's a false and false. Well, that's false. And false and true is false. So take a look at these truth values here and compare them with these truth values here. Can you see that they are opposites? That means that this value right here is a negation to this. And indeed, when we talk about conditionals, if the condition is met and the promise is not kept, okay, then that negates that. So if she wore the red dress and I didn't take her out to dinner, I would be lying. So, take a look at example 1.6. Suppose your basketball coach made the following conditional statement. If you play well in practice, then you will start in tomorrow's game. Well, if you play well, so let's see. If you play well, then you So here's our condition that you play well, and here's our consequent that you will start in tomorrow's game. The only way that the coach could be lying to you is if you play well and you don't start. Okay? If you play well, then you're pretty much guaranteed to start, right? Okay? What happens if you don't play well? Okay? If you don't play well, then the coach can do whatever he likes. He hasn't told you what will happen if you don't play well. He's told you what will happen if you do. So if you don't play well, he could be nice and let you start, or he could be completely within his rights and not let you start. It doesn't matter. He still would have told the truth. He's under no obligation if you don't play well. If you do play well, he is obligated to let you start. Okay. Now, the if-then is a conditional statement. The if-then is a form that it can be used pretty deceptively. So, suppose that you go to a used car dealer and the car dealer said, well, if this car was driven by a little old lady, then it's the best deal you could possibly make. Well, the only way he could be lying to you then under that kind of a statement would be, if the car had been driven by a little old lady and it's not the best deal. But by saying if this car was driven by a little old lady, okay, he could be lying about that first part. He could essentially, a little old lady might not have been driving the car. Might have been a Formula One race driver or something like this. Well, and then, he would still be telling the truth, formally. Okay? You have to watch out how you use conditional statements. Now, what about using this in the idea of deductive reasoning? Well, with deductive reasoning, we draw conclusions from given true statements by rules of logic. Okay? And here we have this statement right here, and let's suppose that we go into the second statement. So here's a statement. We're going to assume that this is true. Okay. If you play well, then you will start. Okay. So we have three possibilities for what will happen. All right, by the rules of logic. If you play well and you start, then that was the truth. Suppose you don't play well and you start anyway, then that's the truth. Well, suppose you don't play well and you don't start, well, that is also the truth. Okay? So, if you play well, then you will start. And the second part of our premises that we talked about, let's suppose we have another statement that says you play well. Okay. Well, then what conclusion can we draw from this? Well, if you play well, then you will start. You played well. Here's the truth value for you played well. Then what's the conclusion? Well, the conclusion is you will start. Okay. Well, what happens then if the second statement is something like you did not play well? Well, here is the situations where you did not play well. Okay? So what can we conclude? Can we conclude that you will start? No, we can't. Can you conclude that you won't start? No, we can't conclude that either. And in fact, under these situations, we have a problem. We have no conclusion. we can't reach a conclusion under these conditions. No conclusion can be reached, okay? Why? Well, the condition was not met. Okay. So, that would mean that if they put down a conclusion, it would not be logically valid. If they had said, well, you didn't start, well, that would not be logically valid, all right? Well, let's suppose we have this, suppose we said, as the second statement, well, if you play well, then you will start, you did not start, okay? So here's our second thing. So, so if you play well, then you will start, okay? And remember, we're looking at this is play well, and this is start, okay? You did not start, okay? Well, where's the place that you did not start? Right there. And what conclusion can we make? Well, that means you must not have played well. So that's a valid conclusion that we can come to. You did not play well. We can look at this from a graphic perspective. Okay, we can say, if you play well, then you will start. You can see that this actually works out as being worth this, because if you play well and start, okay, both of these are true, okay? Suppose you don't play well. Well, if you don't play well, you still have a possibility of starting. But if you don't play well, then you have a possibility of not starting. So not playing well doesn't guarantee that you start or not start. But playing well, being in this group, actually means that you will start. So here's this. So if you play well, then you will start. If you didn't start, right, that means you were out here, that would indicate that you did not play well. So, reasoning can be valid or invalid. This is an example of valid reasoning. And we're working with rules of logic. And so we're going to try a little bit more with, in another segment, about looking at some more rules of logic dealing with these ideas of conditional statements.